about today is what you see here, it's a long title, but just long story short is that I'm a master's student from Kansas State, a master's in artificial intelligence. I just finished my master's and I should be graduating in August. So this was, thank you. So this was actually my thesis, and the reason why I chose to present this is because I used Python a lot for this project. This wouldn't have been possible without Python. So it's a long title, and I'm just going to try to read it. So it's a novel framework for efficient path planning through real-time cost map generation using neural networks for search and rescue missions. Sounds complicated, huh? But I promise you it's not. It's just a lot of words right there. But basically what I was trying to do is, with my thesis is, I was working on search and rescue for robotics, and I was looking at a situation where we could have similar search and rescue. If I don't know about the expertise level of you guys, but if you guys know, reinforcement learning is at the forefront of robotics. And what I was trying to do right here is just challenge the existing reinforcement learning architecture that's been used for robotics. So let's just go into it, right? So as you all know, search and rescue missions are like so critical. As you all know, search and rescue missions are so critical, and time is of the essence. So if you have a group of robots moving within search and rescue missions, they have to move in the fastest manner possible. So what you see right there is just that's an earthquake-stricken region, and trust me, it could get worse than that. This is just to show you the impact. And robotics has come in to save the day because, as you guys have seen with Boston Dynamics, they make really cool applications, and that's just an example of how the robots are actually being used for search and rescue missions. So this piece of research, or this piece of work, was trying to address issues with path planning, because assume you have this region stricken by an earthquake or calamity or whatever that is. The robots need to know where to go, right? And we don't tell the robots where to go. We have to kind of seamlessly program the whole thing to know where, make the robot smart to actually know where to go. So that's what I'm going to be talking about here. So as part of my introduction, data is very important, right? You all agree. They say data is the new oil. And to do this, we needed a lot of data. But to start off, and just to make this as simple as possible, is that we had two types of data, or I tried to generate different types of data. So just a disclaimer, this is all hypothetical. We still haven't deployed this on an actual robot at the moment, but this, I want to take you step by step to see how we arrived at the solution. So we had two things. We had static and dynamic data. So what is static data? This is just based in this context, not what you know about static data. This is just based in this context. So we thought, okay, we have this region stricken by an earthquake or floods or whatever calamity that is, and what kind of data can we get on the ground, right? So this is in relation to the region that's been stricken by an earthquake, right? So we had what we call the topological map features. So assume you have a map of a region that has been stricken, you could actually extract some data from this region. So what are some of these things? And remember, this is in relation to robotics. So if I mention some jargon and you're not familiar, just be sure to ask me a question. So we had all this data, slope data of the region. We had road network data for the region, and we have geographical map features. So geographical map features would be what's actually on that calamity-stricken region. Is it buildings? Is it that kind of stuff? So all that we collected, and we kind of encoded that into a series of numbers. And then we also had dynamic data. So why we call this dynamic data is because it's data that corresponds to the evidence that the robot would actually find in the course of the search. So just assume these robots have, what do you call it, like computer vision capabilities, so they're able to like detect everything and anything that's on the ground. So that's what we call the evidence data. And then what we would do is we would kind of amalgamate these two pieces of data, static data and dynamic data, to get what we call the amalgamated cost map. So if you have a map of Cleveland that's been, or a map of a region that has been stricken by a calamity or whatever, we would actually get what we call the amalgamated cost map of each and every region. So assume that you have this room. So this room would actually be divided into certain regions, and we would have specific values for each and every region, and that's what would actually guide the robot. Sounds complicated, huh? But trust me, it's not. So the ACM that you see right there is what we call the amalgamated cost map, and this is the foundation of this research, of this piece of work, and all this has been done using Python. And so the ACM is what is used by the robot to make path planning decisions. So let's see how. So this is just some related work, what has been done before. I'm not going to go through that because that's just too much jargon. But what I would like to highlight right here is reinforcement learning, because if you guys have some understanding of reinforcement learning, is where an agent actually, what do we call it? Tries to move in the direction of a goal. So if I'm trying to go there, if I'm trying to walk towards that door, I have no business going this direction. So that's kind of reinforcement learning. Like, I would actually go to where my goal is. And it's a good model, but there's like a lot of challenges with reinforcement learning. And that is why I was trying to challenge reinforcement learning through this kind of work, specifically for robotics. And then one of the other things is that when you use reinforcement learning, one challenge is the robotic agent does not have like a global view of the actual region. So that's one of the things that we was trying to capture. Like, if I have a search and rescue region, how can I understand what is going on at that corner without actually being there? So I'm going to show you how. So that's one of the challenges. And then when you think about a search and rescue mission, you have things that you know about the search and the things that you actually don't know about the search. So to do that, we classified this into two broad categories, which is known factors and unknown factors. And what the known factors would be the things or the features that we actually know about the region. For example, distance. What is the distance from this point to that point? What is the terrain of that region? What is the slope? What features do we have on the map? So we would actually encode this on the, using Python, and then we would extract what we call the ACM. So remember, the ACM is what guides the robot to make the path planning decisions. And then we have the unknown factors. These are factors that we cannot account for. For example, weather conditions. Even if you have the best robotic solution and there's a tornado or whatever, it won't work. So we have these unknown factors, environmental hazards, and all that kind of stuff. So these are factors that we could actually not account for, and we had to acknowledge that. So when you have a search and rescue region, how do you know what places you need to prioritize? Anyone? The global population, the local population. Yeah, that's a good point, because if this place was stricken by an earthquake or whatever, in our search we would have to prioritize the region that was actually highly or densely populated. Any other that you could think of? How much damage, and that would be like, for example, if you have tall buildings, that is a region that would actually be, yeah, that's a good point. Yep. Sorry, could you say that again, please? Yeah, yeah, absolutely. So those are like valid points. So as part of this solution, we had to find ways to prioritize regions that would actually need attention first. But the problem is we don't have this data. We don't have this data, and that's the biggest problem. Like I said, if you have a search and rescue region and you don't know what's going on the other end, how would you do that? How would you know what's going on that end if you don't have the data? Anyways, so my main contribution for this was to find a way that I could actually create these data, and in so doing, this could actually be implemented in any kind of search and rescue mission or search and rescue region where you have robotics as a primary solution. So right here, I do have a data generation or data creation technique that can be used for any kind of search and rescue mission. And then right here, the next thing is, what I was trying to do is use a neural network to actually calculate what we call the ACM. And the ACM is the amalgamated cost map, and that's, I would say, these are the values that the robot will actually use to know where to go. And to do that, I'm using a neural network. And the kind of, the neural network of choice was the UNet neural network. Sounds complicated, huh? Anybody knows the UNet? Or anybody knows what a neural network is? Great. All right, so as per my proposed solution, as I mentioned, we have the static data, which is data that corresponds to the actual region. The map features the slope, this would be relevant to the actual calamity-stricken region. And then we have the dynamic data, which is now the data or the evidence data. For example, if a robot was searching this region and found a survivor at a certain region, that would be considered as evidence data. Or sometimes, like what the search and rescuers do is, if I was trying to search in this direction and I found something that might be helpful, like a cell phone, that would actually give me a hint about a possibility of a survivor within the region or a casualty. So I'm just trying to take you guys slow because I know there's a lot to this, but in case you have any questions, please be sure to save those questions for the Q&A. So the static data and the dynamic data, these are types of data that we have actually generated, and then we would actually put these two pieces of data together to get what we call the amalgamated cost map. And remember, the amalgamated cost map is the value that actually guides the robot on where to go given the search and rescue region. So, as part of the solution, as I said, we don't have this data. So what do we do? As part of the solution here, we started off by using some hypothetical findings. I repeat that, we started off by using some hypothetical findings to determine like the hotspot regions. So let me give an example. If you have a calamity-stricken region and you actually have to guess where you could find survivors, would that be a hard problem? Would that be a hard problem? No, because if you have regions or places of human dwelling, that would actually be considered as a hotspot, right? So that's what we did is we used some hypothetical findings for a specific search and rescue mission where we took a map of Kent, Ohio, that's where I'm from, and what we did is since we had some places of human dwelling or places that you're highly likely to get survivors, we'd actually place survivors right there hypothetically and then extract the data and then use a neural network. Trust me, I'm going as slow as possible. Did I lose anyone yet? Awesome. So, as I said, once we extract the data, we would actually use a neural network to generate what we call the ACM, which is the amalgamated cost map. And then through this amalgamated cost map, we would actually, I'm going to show you, I think that should be on the next slide, but we do have a search region that's been divided into like different sections, and all we have is numbers. And then once we have those numbers, we would actually use what we call is an A-star algorithm, which is just a path planning algorithm from one point to another. So in actual sense, once we generate these amalgamated cost map values, we would actually use an A-star algorithm to help the robot move to regions that have the highest amalgamated cost map values, because the higher amalgamated cost map values corresponds to the regions that have the highest priority. And then, so the A-star was very instrumental in this whole process. All right, too much talking, right? So right here, we do have a map of a region. This is the map of, I think, someplace in Kent. And this is just this is just a diagram to illustrate like the whole idea. So assume you have a search and rescue region, which is this right here. So what we actually did is we thought, okay, if you have this as your search and rescue region, what would a human rescuer do? How would a human rescuer start this search, given this region? They would actually go to places that they would actually find people. It's like guesswork, right? Because I think since there's a house right here, there's a high possibility there's a person here, right? So that's what would happen. And what you see, the what do you call them? The person's icon all over the place. First of all, the search region would actually be divided into regions. And why do we do that? Because we want to personalize each and every region. Remember, the end goal of this project was to come up with what we call the amalgamated cost map values, which corresponds to priority. So just to mention, for example, this right here, that spot would actually have a very high amalgamated cost map value because we do have a survivor there, right? Also, we do have findings, or we do have evidence. And what is the evidence? Evidence is anything and everything that would actually lead to a potential survivor, right? If you find, if you're trying to find somebody and you came across their phone somewhere, that would actually give you a hint that he's probably somewhere there. You know what I mean? So that's just it. So all this that you see around, apart from the human icon, that's just all the evidence that we could collect. So we classified evidence as one thing. So given this, we would actually extract the static and the dynamic data, and then we would actually put this together through a function to get what we call the amalgamated cost map. So we would actually understand what's going on. So the robot would actually understand, like, if the robot is actually here, it would actually understand what's, and I say this carefully, possibly, what could possibly be going on the far end. And that's one of the things that we actually look in reinforcement learning. So we had static data, and for the static data, so how we map this is, given this, we would actually extract the static data. And the static data had three things. We had the road network data, so on what specific places can the robot actually pass through, like what are the paths that we have, and then we would actually look at the geographical features, and then all this we would actually put in form of numbers, because all the computer understands is numbers. So we would actually encode this into specific numbers. So for example, if you have a certain geographical feature like a building or something like that, we would actually assign that to a specific value. And then, because remember, this is all data creation, so we acknowledge that some of the things was out of the scope or was out of, we weren't able to actually come up with, and that's the slope. We just can't guess the slope. So we assume that for a search and rescue region, we have just a flat slope, and all we have for the slope data is just one. And then we have dynamic data. So for dynamic data, we had 3 types of data. We had dynamic survivor data, we had findings data, and report information data. So I'm just going to highlight the first 2 because that was the most important, or one of the building blocks for the whole idea. And for the survivor data, any cell or any region that has a survivor was assigned a value of 1, and all the other regions that didn't have a survivor were assigned a value of 0. And then for the findings, we had a range of values from 0.1 to 0.5, and each and every finding on a map, we would actually assign a value between 0.1 and 0.5, depending on the category that it was from. And then, most importantly, is that the evidence data would actually be used to generate what we call the priority table. And the priority table would actually tell you which exact spot requires much attention. So that's how we derive the priority table. That's from the dynamic data. So that's how the data looks like. This is just a basic diagram. So this is just sample data. The slope data, the road network data, the geographical data, and how that came up to that. And then right here, remember when I said about the priority table? So we would actually calculate the priority through a function right here, which is just a weighted sum of each and every value. So remember, we do have the region. Yeah, we do have the region divided into separate, different regions, and then we would actually we would actually arrive at the priority table. Kind of seems my time is up. So that's just the over architecture. But most importantly, what I would actually mention is that we used a neural network to generate what we call the ACM. So we don't have to do this mapping every single time. As long as we have the data collected from the first search region, or for the first scenario, all we had to do is just pass the values, the static and the dynamic values of the actual search and rescue region that we are trying to find, to generate the amalgamated cost map through the neural network. And then just to mention this, the whole process at the end of it all is meant to be seamless. And I think I'm just gonna finish my presentation right there because of time. I know it was quite a lot. Is